Hello everyone, I'm Drew Penney, and today I'm going to talk about principles and prospects of AI applied to computer architecture. In the next paradigm, I envision this as a synergistic loop, not a one-way path. As we will see, this positive feedback loop has exciting possibilities for both machine learning and architecture. Machine learning has rapidly become a revolutionary factor in many fields, ranging from commercial applications to medical applications. This rapid expansion is at least partly due to these models' ability to learn without explicit programming. Instead, these models discover patterns or relationships in data, allowing them to perform well in many tasks, even those too complex to model using more traditional methods. Concurrently, during the past decade, we have witnessed Moore's law slowed down, putting an increasing burden on architects to supplant Moore's law with architectural advances. These two opposing trends between machine learning and Moore's law suggest the opportunity for a dramatic paradigm shift in architecture, in which computer architecture enables machine learning, and simultaneously, machine learning enables computer architecture, closing a positive feedback loop with vast potential for both fields. I'll start with an overview of machine learning principles, including significant models and learning approaches. Next, I'll review machine learning applications to architecture, spanning a broad range of strategies, components, and goals. After that, I'll provide some analysis on these works and identify some best practice techniques that might guide future work. Finally, I'll propose future work towards the next paradigm. These topics will cover a lot of material, but don't worry, since these details and more can be found in our paper. Let's begin with some machine learning concepts. Machine learning has been rapidly adopted in many fields as a solution to a diverse range of problems. This broad scope can be attributed to several factors. Perhaps most significant is the powerful ability of machine learning models to learn relationships and patterns for a wide range of data types and representations. These capabilities result from a generic mathematical framework that allows these models to learn from examples or the environment. Another factor is the broad range of approaches that can be used for a given problem. Consider, for example, the task of IPC prediction for a processor. We could experiment with a simple linear regression model, which learns a linear relationship between features, such as core frequency and cache size, and the target, which is IPC in this case. Using this linear model, the prediction accuracy might be quite high if the system characteristics are relatively linear. Prediction accuracy might not be so great if the system characteristics are more complex. With machine learning, there's almost always another option, such as an artificial neural network. This diversity allows researchers to adjust models, model parameters, and training features to match the task at hand. Choosing a learning approach is another fundamental consideration in any machine learning problem. This choice can be broken into four main categories: supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. These approaches can also be implemented using a variety of models, each with potential strengths and weaknesses based on the task and assumptions about the task. As a general guideline, these approaches can be differentiated by what data is used and how it is used. First, let's talk about supervised learning. Here, the model is trained using input features and labeled outputs, with the result being a model that can predict outputs for new, unseen inputs. Common applications include regression tasks, as in the previous IPC example, and classification tasks, where the model predicts a label, such as optimal core count, for application execution. Although neural networks are likely the first supervised learning model that comes to mind, there are several other common options, including decision trees, Bayesian networks, and support vector machines. Decision trees use a structure where nodes represent features and branches represent a value or range of values for a feature. Consider, for instance, the decision tree shown on the slide. Here, features include temperature, utilization, and injection rate. Starting from the top, if temperature is high, we follow the branch to utilization. If utilization is then low, we follow the branch to the leaf, which represents the final classification of 0.7 volts. These models enable a trade-off between accuracy and overhead by controlling the number of branches per node, as well as the total tree depth. Bayesian networks, unlike decision trees, embed conditional relationships into their structure. In these models, nodes represent random variables, and edges represent conditional dependence between those variables. As a brief example, consider three events: sunshine, a street light being on, and the street being illuminated. The street could be illuminated because either the sun is shining or the street light is on. Further, the streetlight being on is conditioned upon the sun shining, since streetlights are generally off during the day. These models can be scaled, like decision trees, by considering more features and more complex relationships. Support vector machines, or SVMs, are generally known for their function, not for a graphical structure as with the other models. Specifically, SVMs may be considered for their ability to optimize the margins of predictions, essentially learning the best dividing line between examples in a two-dimensional case, or the best dividing hyperplane in the general high-dimension case. While the simplest model variants attempt to separate examples based on linear feature relationships, nonlinear features can also be modeled by using a so-called kernel trick, which maps inputs into a higher dimensional space where a better division can be found. Neural networks are again commonly recognized by their structure, which is reminiscent of neurons in the human brain. Perceptron models represent the simplest case that calculates weighted sums using the inputs and learned values for connections between the input and the output. More complex deep neural networks include many layers of these weighted sums. Additional neural network variants include convolutional neural networks and recurrent neural networks. Convolutional neural networks replace some fully connected layers with convolution operations that consider the spatial locality of features in the input. These models are therefore commonly used in image classification, where it is important to detect edges, shapes, and other local patterns. Recurrent neural networks instead add loops from the output back to the input, allowing better handling of sequences of values or longer patterns in the data. In practice, variants of support vector machines and neural networks tend to perform best for high-dimension and continuous features, and also when features are nonlinear. These models, however, tend to require more data compared to Bayesian networks and decision trees. Next up is unsupervised learning. In contrast to supervised learning, unsupervised learning uses just input data to extract information without any specific output targets. In that sense, unsupervised learning models provide a method to automatically organize or interpret inputs in a way that might not be immediately obvious to a human. One application is clustering tasks. In these tasks, input data can be grouped into clusters based on similarities between features. As we will see, these clustering algorithms have proven quite useful in some architectural applications. Semi-supervised learning represents a mix of supervised and unsupervised learning, with some paired input and output data and some unpaired input data. These models are particularly useful when there's lots of input data, but it would be too time-consuming to generate an output target label for all this data. So far, semi-supervised learning has not found much application in architecture, but it could still be explored. Finally, we have reinforcement learning. This learning approach involves an agent, which is essentially the model we're training, and the environment, which is essentially the system or task that's being considered. In this setup, the agent is first provided with information about the state of the environment. Then, based on this state, the agent makes an action that may change the environment. Finally, a reward is given to the agent based on the usefulness of that action. This process may be repeated many times. These models also often include a discount factor that allows control over how much current rewards are valued in comparison to future rewards. So there are many possible reinforcement learning schemes that provide different approaches to approximate the best action. Q-learning is a noteworthy example in current practice. The Q-learning approach estimates the value, or how good it is, to take a particular action from a given state. Optimal actions are approximated using examples obtained from many states. Implementation, however, requires a table to store all of these pairs of actions and values. An alternative deep Q-learning approach instead uses a deep neural network to approximate the so-called action value function. This can eliminate tables for action value pairs, but introduces storage needs for the neural network weights. Next up, let's review recent research on machine learning applications. Since this section covers a broad range of research, it might be difficult to follow every detail. Instead, just take this as an opportunity to get a general sense of possible applications. The side benefit is that sticking with me through this section will save you months of digging through research papers on your own. So nearly 100 papers are represented by 6 subtopics based on either the specific component or the main objective of that research. Since it's not possible to talk about all 100, I'll instead just focus on a few representative works for each subtopic. So let's start with system simulation. Cycle-accurate simulators have long been the standard tool to evaluate a given system configuration. These simulators require orders of magnitude more time than native execution. Machine learning models can offset this penalty by introducing a trade-off between simulation time and accuracy. Notably, reductions in accuracy can be quite low, on the order of 1 to 5%, while offering potentially several orders of magnitude improvement in execution time. An early example of this machine learning application is provided by IPEC. They trained a group of artificial neural networks using approximately 1% of the design space. Predictions for chip multiprocessor performance exhibited approximately 4 to 5% error on average. Their machine learning-based approach was also shown to combine effectively with SimPoints, which allowed further reductions in the required number of simulated instructions with just a slight accuracy penalty. Implementation flexibility can also be improved by combining machine learning with other techniques. For example, Eiermann considered a mechanistic empirical model to predict processor IPC. The foundation for their model is a parameterized mechanistic framework based on generic CPU behavior. Eiermann then fit these parameters using a machine learning regression model. The resulting overall model was easier to construct than a purely mechanistic framework and provides improved interpretability compared to a purely empirical framework. Another common application is cross-architecture performance and power predictions. Zhang first considered a linear regression model for this task. They profiled Intel and AMD processors while predicting performance for an ARM processor. They later expanded this work to consider program phase-level predictions. Notably, this approach achieves under 1% average error for cycle count predictions and 2.5% error for power predictions. Design space exploration in GPUs is a particularly promising application due to a highly irregular design space. While some kernels exhibit relatively linear scaling, others exhibit complex relationships between configuration parameters, performance, and power. One approach proposed by Wu scaled the number of compute units along with engine frequency and memory frequency. They first obtained data from many kernels for a wide range of design configurations, then used an unsupervised k-means clustering algorithm to determine kernels with similar scaling performance. After that, they trained neural networks to classify new kernels at runtime into one of these clusters based on performance counters such as instruction mix, resource utilization, and memory accesses. GPU-specific cross-platform prediction considers how to estimate the possible speedup from porting code execution from a CPU to a GPU. Baldini cast this problem as a classification task, testing both a modified nearest neighbors model and a support vector machine. Each model predicts, based on a threshold, if GPU implementation would be beneficial. They find that both models can determine a near-optimal configuration approximately 91% of the time. Another approach by Ardelani, in contrast, trained a large ensemble of regression models to directly predict GPU performance. Although several code segments exhibit high error, the model still successfully identifies several code segments that are incorrectly predicted by human experts. Machine learning application for GPUs is certainly not limited to just performance and power predictions. Pat Naik applied several regression models to the task of workload scheduling in a heterogeneous processing and memory architecture. Their architecture integrates a simplified GPU, called GPU PIM, in the base layer of a 3D memory stack. The first step in scheduling is performed by a regression model that predicts processor affinity, effectively determining whether a kernel would benefit from execution on GPU PIM over traditional GPU cores. A secondary regression model is trained to predict execution time for each kernel, allowing dynamic workload redistribution. Recent work at Oregon State University re-evaluated commonly accepted knowledge of GPU traffic patterns. This work used a convolutional neural network and machine learning-based clustering to identify 8 unique traffic patterns with high accuracy. Within the cache hierarchy, work has explored several methods for data prefetching and data reuse, both enabling more efficient cache usage. Peled proposed a reinforcement learning-based prefetcher to exploit semantic locality, which is essentially the locality derived from data structures. Wang instead used a simple decision tree to predict reuse prior to cache entry, and then cache data only when there is predicted reuse. Recurrent neural network-based prefetchers have also been explored. Recent work by Bhatia used a perceptron to filter prefetch requests, achieving higher accuracy than machine learning or traditional prefetchers on their own. Machine learning application to memory controllers was also explored relatively early on, and has since expanded to consider criteria beyond just performance and power. One early example by IPEC proposed a reinforcement learning approach that balances concurrency, delay, and several other factors when selecting memory controller actions. Recent works have also considered reliability. For example, Deng proposed a regression-based framework to dynamically optimize both performance and a minimum lifetime in non-volatile memories. Branch prediction is a particularly notable application that has already seen substantial implementation in real-world devices. Initial proposals provided promising results, but were limited by implementation feasibility due to calculation overhead, even for simple perceptrons. To address these concerns, Santamant proposed SNAP, a scaled neural analog predictor. The perceptron-based predictor features analog circuitry to enable an efficient and practical design, with dot product implemented as a sum of currents. This design was later optimized by Jimenez to achieve further gains in accuracy. Recent work by Tarsa, presented in AIDArc last year, targets difficult-to-predict branches using convolutional neural networks, which provides a new potential area for exploration. The dynamic nature of networks on chip, or NOCs for short, lends itself naturally to proactive machine learning-based control, in contrast to largely reactive traditional schemes. Recent work by Fettes explored NOC DVFS with several different linear regression-based schemes, as well as a reinforcement learning model using a deep Q network. For the linear regression schemes, they considered predicting buffer utilization or a change in buffer utilization. The reinforcement learning approach instead uses rewards based on buffer utilization and energy. Machine learning applications for flow control mainly considers optimizing performance by managing resource allocation. For example, Dia proposed the use of Q-learning to handle injection throttling in a bufferless multi-hop NOC. Using this approach, their model learned to maximize multi-hop performance and efficiency by limiting contending flits, while also considering fairness. This mechanism is shown to be very effective, enabling nearly a 35% reduction in latency for a 64-node NOC. Several works have also applied machine learning to higher-level NOC design. Das first considered Stage, a machine learning-based enhancement to hill climbing to generate 3D NOC designs. This Stage framework is later expanded by Jordar to handle multi-objective optimization, again in a 3D NOC, but now in the context of a heterogeneous system. This extension allowed them to consider trade-offs between CPU latency, GPU throughput, as well as thermal and energy constraints. Recent work at Oregon State University on routerless NOCs instead used a deep reinforcement learning framework to explore loop placement in a broad design space. Notably, this framework successfully explores a design space of more than 10 to the 100 and has broad potential applications. Beyond performance predictions and energy optimization, there's also a need to consider NOC reliability, which involves schemes to correct errors during NOC traversal. Machine learning approaches allow these schemes to be dynamically chosen to reduce overhead while minimizing latency. Wang adopted a reinforcement learning control policy that proactively determines the required encoding scheme and thereby achieves an average of 46% dynamic power savings compared with static schemes using a cyclic redundancy check. Energy efficiency optimization has become a significant consideration in architecture due to the growing gap between computation resources and energy limitations. Wang addressed this problem using a hybrid control scheme that combines an artificial neural network and a PI controller. This hybrid scheme allowed the PI controller to act as a surrogate for supervised training data during online learning. Once the neural network has had time to train, control can then be dynamically passed between the PI controller and the neural network. Bai implemented a reinforcement learning policy for a novel voltage regulator hierarchy using off-chip switching regulators and on-chip linear regulators. This hierarchy allows a control interval of 1,000 committed instructions on a core, allowing the reinforcement learning agents to rapidly converge to high-quality control policies. Machine learning models have also shown strong performance in task allocation and resource management due to their ability to consider the long-term impact of actions or configurations. This advantage was observed by Liu, who proposed a thermal-aware reinforcement learning method for task allocation. Comparison with a heuristic algorithm shows temperature reductions of up to 8.1 degrees Celsius in some workloads. More recent work by Chen considered adaptive co-optimization for several resources, including caches, cores, and the NOC using reinforcement learning. They emphasized the potential improvements and increased configuration flexibility by co-optimizing several components using one model, rather than optimizing these components individually. Wu demonstrated uses for machine learning in chip layout, deviating from the common applications including control prediction and design space exploration. They used k-means to cluster flip-flops during physical chip layout in order to minimize clock wire length at the expense of signal wire length. They also integrated constraints for maximum flip-flop displacement and cluster size. The resulting configurations successfully reduced displacement, total wire length, and total switching power compared to the prior approach. Machine learning applied to approximate computing thus far focuses on function approximation and the need to ensure overall quality. One notable implementation is the Neural Processing Unit, or NPU, proposed by Esmailzadeh. They replace approximable code segments with neural processing invocations, essentially translating the original code into a sequence of neural network operations. They find that average application error rates can range from 3 to 10%, while observing a 3 times average reduction in application energy and 2.3 times average application speedup. This approach performs well when code segments are easily approximated, but does not provide great control over cases where a particular input leads to high error. For that reason, Mahajan introduced Mithra, a co-designed hardware and software control framework for neural approximation. Mithra implements configurable output quality loss with statistical guarantees in 2 steps. First, an error threshold is determined using statistical analysis on a representative input set. Next, this threshold is used, along with approximated results, to train a binary classifier based on whether an input, when run on a neural accelerator, would exceed the error threshold. They considered both a table-based classifier and a neural network classifier, and find that both classifiers still achieve high average speedup and energy reductions, even with restrictions on overall quality loss. With all these broad applications in mind, we can pick out some potentially useful practices for future work. I divide work into 2 categories based on design constraints and operating timescales, and therefore different design practices. The first category, online ML application, includes work that integrates machine learning at runtime, even if training is performed offline. Design complexity in this work is therefore inherently limited by practical constraints such as power, area, and real-time processing overhead. The second category, offline ML application instead applies machine learning to support architectural implementation, involving tasks such as design space exploration and simulation. Consequently, models for offline application can exploit higher complexity and higher overhead options at the cost of training and prediction time. Supervised learning approaches in online applications primarily use either decision trees or artificial neural networks, while reinforcement learning models use either Q-learning or deep Q-learning. Applications for these models, however, are not necessarily disjoint. DVFS control work by FETAs is an exemplar, which tests both supervised and reinforcement learning approaches. Both schemes can perform well, but the reinforcement learning scheme is found to be more flexible since the energy and throughput trade-off can be tailored to application needs and does not require threshold tuning. This advantage, however, does not imply that reinforcement learning is a one-model-fits-all solution. One example is function approximation, which naturally pairs with supervised learning, since this task is not easily represented as a sequence of actions. Implementation and overhead limitations for online applications are also highlighted in several works. For example, NOC-based works have applied different methods for global data collection to support machine learning models. Dia-controlled injection throttling using data from a separate starvation network. WAN instead encoded data into unused bits in standard packet headers, then opportunistically collected data as it is passed through a central unit. This approach introduces potential concerns about staleness, but prior work observed limited impact for large control windows. Implementation can also consider the use of either hardware or software models. Both hardware and software implementation for neural function approximation were considered by Esmelzadeh, but they observed a prohibitive increase in instruction count using a software implementation. WAN observed a similar trade-off, but chose to implement an artificial neural network in software using an on-die microcontroller. Cycle count for predictions is several orders of magnitude higher, but is acceptable for their application and avoids additional power consumption. Specific hardware implementation approaches may also vary based on the task. A standard artificial neural network implementation by Sava incorporated a finite state machine for control, an array of multiply-accumulate units for calculation, a register array to load and store results, and a lookup table-based activation function. This implementation contrasts with a mixed analog implementation for perceptron models proposed by Saint-Amant. Variants also exist for reinforcement learning models. The standard Q-learning implementation requires a lookup table for action value pairs. Instead, IPEC, as well as Mukundan and Martinez, used CMAC tables, which replace Q-learning tables with multiple coarse-grain overlapping tables. Optimization is particularly important for online applications that also train online, since low model accuracy, especially at the start of execution or during periods of high execution variance, can degrade performance significantly. Some reinforcement learning-based work mitigated the impact of poor actions by introducing shadow operations. These operations are still used in model updates, but are not actually executed by the system. Consequently, the model still gains feedback on its actions without actually negatively impacting the system. In a supervised learning setting, WAN trained their artificial neural network online using control actions made by a PI controller, which exhibits far less startup delay. Offline applications generally exhibit higher model and feature diversity, since the model itself is not tied to a specific architecture. Design space exploration, in particular, has been addressed using several different models. The stage algorithm, used in several 3D NOC works, uses an iterative search to generate new NOC topologies by sequentially adding and removing links to find locally optimal designs. The overall search space is then pruned by a machine learning model that learns to predict good starting points for local optimization. Our own research at Oregon State University used a deep reinforcement learning model that also follows an iterative approach to add loops to a routerless NOC design, but instead uses a neural network to also suggest actions. System-level design space exploration has favored more standard supervised learning approaches. Specific model choices may of course still vary, with some linear and some nonlinear regression models, as well as some random forests and neural networks all finding implementation. As in online applications, some tasks are naturally limited to supervised learning methods. Cross-architecture prediction is one example. Optimization in offline applications primarily focuses on improving data efficiency and overall model accuracy relative to traditional approaches. Ensemble methods, for example, can scale to be arbitrarily large relative to computation resources. Several works have therefore considered ensemble-specific optimizations. Julia trained many neural networks using slightly different configurations and generated a high-performing ensemble using the best subset of the individually trained models. They further introduced outlier detection by filtering out predictions that differed significantly from the values in the training set. A different approach by Ardolani instead uses all 100 models that they trained, noting that some models may be strong predictors in one application, but weak predictors in others. They remedied this dilemma by selecting only the 60 closest individual predictions to the median prediction. Other work optimizes the sampling method. Sanghaya considered potential systematic biases in their models, observing that uniform random sampling does not adequately capture relationships in a non-uniform space, such as in cache configurations using powers of 2 for sizing. Powerful relationship learning capabilities of machine learning algorithms enables black box implementation without considering task-specific features. This isolated approach, however, can fail to capitalize on additional domain knowledge that can improve interpretability or model performance. One approach to integrate domain knowledge uses mechanistic empirical models, combining a domain knowledge-based mechanistic framework with empirical machine learning capabilities. Specifically, these models can simplify implementation and avoid incorrect assumptions in purely mechanistic models, and can offer higher accuracy than purely empirical models by avoiding overfitting. Eiermann also demonstrated how these models can be used to identify components with high contribution to execution time, allowing more meaningful alternative design comparisons. Task-specific knowledge can also be applied to features and results. Deng, in work predicting non-volatile memory write strategies, presented a case to tune features based on task-specific domain knowledge. Following initial analysis, they discovered that a single configuration parameter can result in high complexity and therefore lower prediction accuracy, even with relatively complex quadratic regression and gradient boosting models. They addressed this issue by simply excluding the parameter from initial modeling, and then later applying it back to the predicted optimal configuration, resulting in a 2 to 6% improvement in prediction accuracy. Ardolani examined inherent imperfections in their learning model for cross-platform predictions. Some predictions can be easy for machine learning models and hard for humans, representing, of course, an ideal scenario for application. The converse, however, can also be true. In both cases, machine learning application can be strengthened by considering task-specific characteristics. Now let's discuss the future of this field. Specifically, what are some implementation strategies or applications that are worth considering in future work, and in the longer term, where is this field heading? First, we can consider new strategies for implementation to improve the overall utility of these models. As discussed earlier, model complexity can be a limiting factor in online machine learning applications. The standard Q-learning approach requires a potentially extensive action value table, while neural networks require storage for their connection weights. Implementation using neural networks has only been possible in existing work by restricting the model to just a few layers. Recent research, however, has demonstrated promising results to reduce model complexity through pruning. This process eliminates unnecessary connections and can achieve greater than 90% sparsity with little accuracy penalty. So, can we then use this capability to address more complex tasks by training larger models, and then prune them down for practical implementation? Next, we can consider improving applicability using newer models and techniques that are better suited for the characteristics of actual program execution. Hierarchical models are a noteworthy example that has only recently been considered to enable a broader scope for predictions and control. Hierarchical models for reinforcement learning, in particular, could be applied to co-optimize control policies that consider both the lowest level details of packet routing to the highest level details of workload scheduling, for example. In addition to newer models, several works have already demonstrated high performance using phase-level prediction and control schemes. The overall objective is to identify and make predictions or control actions on a finer-grained timescale that better matches actual program execution. Application at the nanosecond scale, for example, allows even the most brief periods of high energy consumption to be optimized. Another potential aspect for future work is the development of generalized tools and frameworks. My experience as someone with a primarily hardware background was that I had ideas for applications, but was unsure how to go about actual implementation using machine learning. Existing software libraries for simpler models, such as decision trees and spore vector machines, are highly beneficial, but these libraries still have their limitations. Rather than introducing individual models for every task, we should instead introduce more general frameworks that can be applied to more specific design aspects. I view our deep reinforcement learning framework for NOC design as just one component in making this field more accessible to encourage broader application. Perhaps the broadest opportunity is simply in exploring altogether new areas for machine learning application. One such promising application is in emerging technologies and architectures. Several works have established how these new technologies often exhibit issues relating to either performance or reliability. Whereas a heuristic policy may struggle to establish an optimal balance between these criteria, machine learning models can offer highly advantageous control policies by proactively and dynamically adjusting to workloads. Similar benefit is observed in emerging architectures, where development of heuristic policies may be hindered due to the lack of best practice knowledge. Future work can also consider extending approximation to the system level by co-optimizing several approximate techniques, such as reduced DRAM refresh rate and algorithm-based loop skipping. Existing compiler-based works rely upon heuristic searches to determine the overall combination of approximate schemes for execution. Naturally, a reinforcement learning model, for example, could provide more intelligent exploration that can scale along with future high-dimension approximation options. Without a doubt, the most promising option is the long-term prospects for machine learning applied to architecture. Several recent works in particular have already begun to explore broader design and optimization strategies. Research in this direction might be dramatically empowered by newer hierarchical models that can already effectively address both low-level and high-level design aspects. Work towards more automated architecture design can also consider if machine learning models can learn from descriptions of architectures, or perhaps even directly from research papers on architecture, in order to gain insight from the most effective human efforts to improve architecture in past works. Machine learning has rapidly become a powerful tool in architecture, with established applicability to design, optimization, simulation, and more. Notably, machine learning has already been successfully applied to many components, including the core, cache, NOC, and memory, with performance often surpassing prior state-of-the-art strategies. These advancements are likely just the beginning of a revolutionary shift in architecture. Opportunities for optimization at the model level offer potentially broad benefit for many tasks. Similarly, there are many opportunities to extend existing work using ever more powerful machine learning models, enabling finer granularity, system-wide implementation. Finally, machine learning may be applied to entirely new aspects of architecture, learning hierarchical or abstract representations based on both low and high-level details, or maybe even just based on ideas. These extensive opportunities, along with yet-to-be envisioned possibilities for application and implementation, may eventually close the loop on highly, or even fully, automated architectural design. References for all these works are included here in the slides.